We now turn our attention to polyatomic ideal gases, and after a few comments on the general case of polyatomic molecules, we are going to treat explicitly diatomic gases. For polyatomic molecules, we know that the configurational part of a molecule's microstate contains information about the position of all its atoms. So here is an example, a very simple molecule, ethane. If I want to know the configurational part of the microstate, really this is just by definition the positions of all the atoms of this molecule. So I have to specify 3 times m positions of atoms. In this case, my ethane is made up of 2 carbons and 6 hydrogens, so a total of 8 atoms. So if I know the positions of these atoms, I know the configuration of the molecule. Equivalently, I could have specified some different degrees of freedom. So instead of specifying the positions of the atoms, I could specify these 3 things. First of all, the position of the center of mass. And this, in the 3-dimensional space, would give me 3 translational degrees of freedom in the x, y, and z coordinates. Then I could specify the angles of rotation with respect to these 3 axes. These are rotational degrees of freedom, again with respect to the x, y, and z axis. And finally, I have some internal coordinates. So I have, well, the remaining coordinates are internal coordinates, 3m minus 6 coordinates, which are basically vibrational degrees of freedom. So these could be, for instance, the bond distances between this hydrogen and this carbon here, the same here, here, etc. These degrees of freedom can be assumed to be decoupled, and this is a pretty good approximation typically. So the partition function for a simple molecule can be written as follows, as a product of the quasi-partition functions for the translational degrees of freedom, the rotational degrees of freedom, and the vibrational degrees of freedom. So this is just for one molecule, a polyatomic ideal gas molecule. And if we have a population of n molecules, then the partition function of the polyatomic ideal gas that contains n molecules would be 1 over n factorial times the partition function of the one molecule raised to the nth power. So remember, we assume that there are no interactions. This is an ideal gas, and we assume that we have indistinguishable molecules. Well, this is obviously this is a good assumption, right? So this n factorial is just enumerating the number of ways I can label my particles. So this term 1 over n factorial corrects for the overcounting because of that. So we've already learned the translational partition function, so we know how to calculate Q trans in this case here. So now we're going to look into the rotational and the vibrational parts, focusing on a simple case of a diatomic molecule, which has 3 translational degrees of freedom and also 2 rotational and 1 vibrational degree of freedom. By the way, as homework, I would like you to consider the following question. Would the ideal gas equation still hold? Right, so we recovered in the previous part of the lecture, we recovered the ideal gas equation for the monoatomic gas. Now that you have polyatomic gases, would the ideal gas equation still hold? Yes or no? And I would like you to prove your assertion, so justify your answer. So let's start discussing the rotational partition function of a diatomic gas, like this carbon monoxide molecule over here. We will treat this as a quantum rigid rotor, and you hopefully remember from your quantum mechanics that we have one quantum number here. So this is the angular momentum quantum number, and the energy levels are given by this equation, where h bar is the reduced Planck constant which is equal to the Planck constant divided by 2 pi. This I is the moment of inertia, and here is our quantum number, and each one of these levels has a degeneracy equal to 2 times L plus 1. Now, the rotational quasi-partition function is simply expressed as follows. Again, we are in the canonical ensemble, so we just sum over all the possible states terms that look like this. And you notice now that I put the degeneracy over here because each one of these energy levels, right? So I'm summing for L greater or equal to 0. So each one of these states here has a degeneracy of GL. So this is what my quasi-partition function expression becomes. So this is an expression, is a sum that is not easy to treat, right? When you substitute the expressions for the energy and the degeneracy, you get quite a difficult to treat analytically sum. So we can convert it into an integral by making the assumption that the spacings between the energy levels are small compared to kBt. So we're operating at sufficiently high temperatures that we have a continuous spectrum of energies. That's the assumption. So then this can be approximated by an integral. This is usually a good approximation, except for the case of hydrogen. So the quasi-partition function for the rotational part is approximated by this integral over here. So this is an integral over dl, right? L was our quantum number. So now let's see how we can treat this. We can make the substitution, the change of variables, to get rid of this term because it has this quadratic term over here, L squared. So we would like to simplify a bit our life. So we define a new variable, L times L plus 1. This is the differential. So then if we make the substitution, note that this 2L plus 1 is conveniently appearing here. So then this whole thing becomes this integral, which is a very simple one. Right, so this is e to the minus constant times the variable, d variable. So this is quite easy to treat. If we do the integration, this amounts to 2 times I divided by beta, the inverse temperature, times h bar squared. And of course, here I just made the substitution, right? So beta is 1 over kT, so I get this. Now, we can define a rotational temperature, and this rotational temperature is basically equal to that. So when we do this, then we very much simplify the expression for the rotational quasi-partition function to temperature divided by this rotational temperature. Now, this equation is valid for a molecule that looks like this. So this is a heteronuclear diatomic molecule, right? We have carbon here, we have oxygen there. If you're dealing with a homonuclear diatomic molecule, like bromine or chlorine, etc., then you have to divide this by the symmetry number. So in this case, your rotational partition function will be the temperature divided by twice the rotational temperature. And in general cases, you're going to see this as a sigma, right? Where sigma is the symmetry number. So in this case, sigma is equal to 2. Let's now move on to talk about the vibrational partition function of the diatomic gas. We're going to treat the system as a quantum harmonic oscillator. So basically we have the two atoms that are vibrating, and the energy with respect to the positions or the distance of the two atoms, the bond length, is following some sort of harmonic potential, right? This quadratic potential here. So we're going to treat the system as a quantum harmonic oscillator, and you might remember from your quantum mechanics that the energy levels are given by this equation here. First of all, these are non-degenerate energy levels. They're indexed by this quantum number. I denote it here with nu. So the energy of the nth energy level is equal to h bar times omega, the angular frequency, times the quantum number nu plus 1/2. Now, you might have noticed that we have used the bottom of the well as the reference energy, right? The bottom of the well here. So in this case, the ground state is higher in energy by this term here, 1/2 h bar times omega. So this is referred to as the 0-point energy correction, right? And it's precisely the difference between the ground state energy minus the energy at the bottom of the well. So in this setup, the vibrational quasi-partition function is equal to this sum, where nu goes from 0 up to infinity, and we're summing terms that look like e to the minus beta inverse temperature times the energy given by this equation. Since the energy levels are degenerate, you see that we don't have any degeneracy factor over here. This is just 1. So when we substitute the energy levels in the equation that we just saw, we get this expression here. And this is actually easy to treat because we know that this is a geometric progression. It is a geometric progression because we have e to the minus something, which can be taken out as a constant. And then we have this nu over there, which goes from 0 up to infinity. So recall the sum of infinite terms in the geometric progression. So if we have a geometric progression with the first term being equal to alpha, and then the ratio is equal to r, then this sum is equal to alpha divided by 1 minus r. So in our case, let's try to rewrite this expression so that it's very clear as to what this alpha is and what the r is. So I'm just rewriting that expression as follows. So e to the minus 1/2 times beta times h omega. Recall that this is the 0-point energy correction times beta, right? Times this sum of infinite terms. So what remains here when I take this term out? Simply e to the minus beta h omega, right, to the nth power. So here is my alpha in the formula of the infinite sum of terms of a geometric progression, right? This is my alpha, this is my r. So then this infinite sum becomes is equal to this e to the minus beta times the 0-point energy correction divided by 1 minus e to the minus beta h omega. Now, at high temperatures, we can introduce an approximation. So high temperatures means T temperature goes to infinity, and therefore inverse temperature, 1 over kT, goes to 0. So since this goes to 0, right, and beta appears here, we can introduce Taylor expansions of these exponentials. So this e to the minus 1/2 beta h omega is equal to this sum of terms, right? So for beta equals 0, this is equal to 1. And then we have the derivative of this times beta, the second derivative evaluated at beta equals 0, right? Divided by 2 factorial times this, etc. Right? So this is the quadratic term, the cubic term, etc. So we have an infinity of terms in the Taylor expansions. Of course, we're going to deal with only a small number of terms. We do the same for the exponential that appeared in the denominator of the partition function expression. So we find something that looks like this. And then we only retain the leading terms. So in the partition function. So in the, right, remember this was the expression of the partition function. So in the numerator, we're going to return terms up to 1. In the denominator, we're going to retain terms up to the linear term. Why? Because this is 1 minus this thing. So obviously, if we returned only this term, that would give a singularity, right? So we also need to take into account the linear term. So this thing, this is the leading term for the expression in the denominator. So this means that at high temperatures, the vibrational quasi-partition function becomes equal to 1 over beta h omega. I substitute beta with 1 over kt, and I get this expression here. Right, so this is the expression of the vibrational partition function at the limit where the system approaches high temperatures. So we have to be a bit careful. We said that the temperature, when the temperature goes to high values, then we get this expression here. However, we shouldn't forget that this approximation of the potential as a harmonic potential is not valid at very high temperatures. In reality, if you're looking into the potential that can express how atoms with bonded atoms are behaving, the, let's say, quote-unquote correct potential or a more realistic potential would be a potential like this. This is the Morse potential, which allows for the dissociation of the bond. Right? You see that in this potential with the black, when the distance between the two atoms becomes very, very large, then the potential at some point becomes flat, which means that the atoms are not interacting with each other anymore. Now, on the contrary, the harmonic potential, you see that the energy goes to higher and higher values as the distance between the two atoms increases, and obviously this is not realistic. So when we say high temperatures, we mean high temperatures but not high enough so that the harmonic potential becomes a bad approximation of the real potential. So we have to be a bit careful about that, and always keep in mind that the harmonic potential approximation is invalid for very high temperatures, in which we start sampling the anharmonic region, as it's called, or even start having a dissociated state. Right? Our carbon monoxide molecule, for example, is not carbon monoxide anymore. It's just an atom of carbon, an atom of oxygen, far away from each other, not interacting. So just keep this in mind. We are now at the position that we can put everything together to find an expression for the thermal energy of the diatomic gas. So let's focus on a single molecule. We have already seen this result. So this was the thermal energy because of the translational degrees of freedom. And we had seen in the previous part of the lecture that this is equal to 3 over 2 times kBt. Next, let's treat the rotations. So again, right, remember from a previous lecture, this is the expression for the thermal energy minus d log partition function of the canonical ensemble, d beta, the inverse temperature. So if I substitute this expression here, this is what we found after applying the approximation of small spacings of the energy of the rotational modes. So of course these things are constant, so when I break the logarithms they just go away after differentiating. Then I have a minus over here, so I will have minus log 1 over beta, and this minus goes into the logarithm and inverts this. So eventually I will have d log beta, d beta, plus some constants that get away after differentiating. So finally, it's just this whole thing amounts to the derivative of log beta, which is simply 1 over beta, which is simply kb times t. So the above two contributions give the hopefully well-known result. You should remember this from your thermodynamics courses. So this is the result, that the CV of the ideal diatomic gas is equal to 5 over 2 times R. Yeah, so in this case, if you sum these up, you're going to see that the thermal energy is 5 over 2 times kBt, right? And then the CV, if I want it in units per mole, then this would be 5 over 2 times R over here. Now this is valid at intermediate temperatures. Why? Because at intermediate temperatures, not too high temperatures, the only modes that are excited are translational modes and rotational modes. So what happens at higher temperatures? Well, at higher temperatures, additional contributions arise from the kinetic and potential energy of the vibrations. So we have already seen this expression for the vibrational quasi-partition function. And the contribution to the thermal energy of our gas would be equal to this derivative over here. We know that temperature has to be large enough so that the vibrational modes are excited, but not too large so as to start sampling the anharmonic region or to completely dissociate the molecule. Remember the discussion about the this issue with the high temperatures and the fact that the harmonic potential is not very accurate, a very accurate representation of what happens within a bond. The bond can dissociate, so we have more realistic potentials like the Morse potential, to which the harmonic potential is only an approximation. Okay, so provided that the temperature is large but not too large, then let's try to calculate this contribution, right? So we're going to take the limit of high temperatures that we saw earlier as well. Remember, we introduced these Taylor expansions here for the exponentials, etc. And then we found this limiting result. So again, we see that we get an expression similar to what we had before for the rotational partition function. So the thermal energy contribution from the vibrations is 1 over beta, which is equal to kBt. In this temperature regime, right, high temperatures but not too high, so we still have the diatomic molecule, we get the Cv to be equal to 7 over 2 times R. Right, so we had a 5 over 2 factor from the previous two contributions, translations and rotations, and then we have one more contribution, kBt, which contributes one factor, one more factor, so 5 over 2 plus 1, 7 over 2 times R is the Cv of the ideal diatomic in this temperature regime. So we have now derived a model for the heat capacity of the diatomic molecule, and let's see how well it can describe the heat capacity of a very well-known molecule, carbon monoxide. So what I'm plotting here is the heat capacity under constant volume for CO with respect to temperature. And this is temperature divided by 1000, right? So this is approximately 300 Kelvin. This is 1000 Kelvin, 2000, etc. So there are several curves here and some lines. So let's look at this line first. This is the theoretical prediction that includes only translations and rotations. Right? The expression was 5 over 2 times Kb. That was the prediction for Cv. So we see that this is a pretty good prediction at this low temperature of around 300 Kelvin. That's fine. Then this second dotted line is for the high temperature region, and this is the theoretical prediction that includes translations, rotations, and vibrations. So this was this expression 7 over 2 times Kb, and we see that this, right, so this is the line, and we see that this blue line here approaches this value at high temperatures. What is the blue line? This is the theoretical expression for translations, rotation, and vibrations, but in this case the vibrations have not been assumed to go to the high temperature limit, right? So I have used the explicit expression for the vibrational partition function without making the assumption of high temperatures, and we see that this blue line indeed tends to this dashed blue line at high temperatures, so this is fine. Now, what about the real data? So this is the real data from the NIST webbook, the red line. So we see that the blue line, which is the prediction of the theory, right, the most accurate prediction from the theory, and the red line, they are almost indistinguishable up to a bit more than 1000 Kelvin. Then we see that the blue line tends to the theoretical limiting value for high temperatures, 7/2 times Kb, whereas we see that the data shows that the heat capacity is slightly higher than what the theory predicts. So I would like you to think about why this happens, and we can discuss this in class in the tutorial. Also, I would like you to make similar plots for other molecules, other diatomics, like NO, O2, chlorine. Note that for these, because they are homonuclear, you have to take into account the symmetry factor. And I would also like you to check the data with the NIST webbook. And again, we can discuss in more detail during the tutorial. I would like to end this part of the lecture with a quick note on a famous theorem called the equipartition theorem, or the law of equipartition, or the equipartition of energy. So these are all different names for the same thing. And this theorem is really the conceptual generalization of the formulas that we just discussed. Remember that we saw some terms like KBT appearing when we tried to find the contributions of the rotational, vibrational, etc. Modes into the energy of the system. So here is what the equipartition theorem states. In thermal equilibrium, any degree of freedom, such as the component of the position or velocity of a particle, degree of freedom that appears only quadratically in the energy, has an average energy of 1/2 kBt and therefore contributes 1/2 kB to the system's heat capacity. So it's easy to verify that these degrees of freedom that we talked about appear quadratically in the energy. So if you go back to the Hamiltonian, you're going to see, for example, that let's talk about the velocity. So the velocity of a particle appears quadratically, right? We have kinetic energy of 1/2 times the mass of the particle times velocity squared. So we have three velocities in the x, y, and z direction, and that's why we had 3/2 times kb being the contribution due to the translational degrees of freedom. Then for the rotations, we have a similar expression. So again, something that appears quadratically. And for the diatomic molecule, we had two possible rotations, right? A rotation along the x-axis, a rotation along the y-axis, and I'm assuming that the molecule is oriented along the z-axis, so there is no other rotation. So 2 times 1/2 kb, right? Exactly kb was the contribution to the system's heat capacity because of the rotations. And similarly for the vibrations, we had position and velocity. In that case, if you think in terms of the classical case, so again we're going to have 2 times 1/2 kb. So kb is the contribution to the system's heat capacity because of the vibrational degree of freedom, the one vibrational degree of freedom that has potential and kinetic energy, and right, so these amount to kb being the contribution because of that. So we have investigated the statistical mechanics of ideal gases, and in the next part we're going to start treating problems in condensed matter, starting with something very simple first, namely non-interacting adsorbates on the edge of a catalytic nanoparticle.